right, so welcome everybody. Thanks for attending my talk. Today I'm going to present some work that is joint work with my supervisor Helmut Seidl. And we're going to go, as we've already said, to weakly relational domains. The conventional wisdom is that they offer a good trade-off between precision and efficiency, and for this reason have been widely used in static analyzers. And one that we've already heard of a couple of times today is the Octagon domain, which is one that's particularly common. It was invented by Antoine Minet somewhere in the early 2000s. For those who do not know, when you have an octagon, what you have is you have a conjunctions of inequalities of this form plus minus x plus minus y is less or equal than some constant c, where c in this case here would be from the integers. So an example octagon value might be something like this, where you say minus x is less or equal than minus 5, x is less or equal than 10, and then you also have some constraints on the sum of x and y and the difference of x and z. Alternatively, if you do not want to talk about integers, you can also talk about octagons that range over the rationals. In this case, your constant would also be replaced with a constant that comes from the rationals. A key operation that one needs to do with octagons is called normalization or closure. And the idea is that one tries to make all the implied relationships explicit. And this is needed, for example, to efficiently check equality, inclusion, and a couple of other operations. Let's take a look at an example here. So if we have this octagon value here, we actually have some additional relationships that are implied. Namely, if I take these two together, then I get an upper bound for the value of y. And if I consider those two, then I additionally get an upper bound for the value of minus z. And this value that we have here would then be closed. Now, the complexity of this operation, it was already known right from the beginning that it's cubic for octagons over the rationals. And then a bit later, or 7 years later, it was shown that it's also cubic for octagons over integers. And Enea is one of the co-authors of this, so he's actually here. And what all of these algorithms have in common, the proofs, is that they tend to introduce auxiliary variables minus x for the negated value of the variable. And then they all employ some sort of all-pairs shortest path algorithm, such as Floyd-Warshall algorithm. And our idea here was somehow that we wanted to raise the abstraction level of these proofs to maybe get at more concise proofs. And particularly, we somehow wanted to avoid introducing these auxiliary variables. And let's first get a bit of notation out of the way. So when we say R, this is a relational domain, then we have some set of variables x. And what will be of particular relevance later in this talk are the clusters of size at most 2. So this is what we mean when we write this x in these square brackets sub 2. So this is all subclusters that have 1 or 2 elements. Then we're going to be dealing with assignments later. So this we don't denote like this, where we say we assign to a variable x some right-hand side e. Then we also deal with guards. This we denote by this question mark c. And then last but not least, we also need to deal with an operation that we call the restriction. And basically this amounts to forgetting all of the information about the variables that are not in this y. And then sometimes we will also use this notation, so R superscript y, to talk about these values that only contain information about variables from the set y. And basically what this means, if I take a value from this and I restrict it to y, then I end up with the original value that I had. So back for some ESOP paper, we at some point made this observation that any relation can be approximated by meeting together its restriction to 2 clusters. So this equality here holds. For some domains, however, one can do better. Namely, one can have some domains where one can give all values of the domain basically as the meet of these restrictions. So one doesn't lose anything by considering only these restrictions to 2 variables. And this then we dubbed to be 2D decomposable. This is the first property, and the other property that one needs for a domain to be 2D decomposable is that all the finite least upper bounds can be computed cluster-wise. This is this property that we have written here. And then we would call basically this restriction to these 2 clusters the 2 normal representations, a bit of notation again. And for octagons, this then corresponds to the strong, respectively the tight closure, this 2 normal representation. Now our idea was maybe if we have this 2 decomposability, we can already do the efficient normalization. And we got inspired by all the previous work that uses some sort of all-pairs shortest path algorithm. So we tried to apply the Floyd-Warshall algorithm here. And the idea would be that we would be given some values that talk about these 2 clusters. and then ideally the algorithm should compute the two normal representation. We discovered quite early on that this does not work right off the box because we have these single value clusters that only talk about one variable, and they somehow destroy this here. So one needs to add an additional initialization loop before, and then this approach seems to work for the octagons. However, we had a very, very hard time trying to prove that this actually computes the normalization for all of these 2 decomposable domains. And then at some point we decided, okay, maybe we should also consider if this is maybe not true and we're missing something here. And it turns out there's a counterexample. So there are 2 decomposable domains where Floyd-Warshall does not compute this 2 normalization. So let me very quickly give you this counterexample. So it's a very simple domain. We basically here fixed a set of variables to be 4 variables. They range over values from this set 1 to 3. And as the abstraction of these concrete values, we consider maps from variables to sets of these values. So for example, one could imagine an abstract value given by these clusters. So in the Rx cluster, we know that A is in the set 1, 2. In the AY cluster, we know that A is in the set 2, 3. And in the AZ cluster, we initially know that it's in the set 3, 1. And all of the other clusters initially are top. And now the 2 normal representation of this should be bottom in all clusters, because if I do the intersection of all of these sets, then I find out that actually there is no value for A that satisfies all of these requirements, and therefore the value should be bottom. Let's take a look at what the Floyd-Warshall algorithm actually does here. So first of all, we have this initialization round. In this case, it does nothing because we do not have any interesting values in this single clusters. So this is done. And then we try to make all of the improvements explicit that happen via this A variable. So what happens here is also nothing. And then we consider the improvements that happen via X. So basically, we consider if I go from A to X, and X to A, what is the value that I get then? And then I project it to just A and meet with the value I had before for A. So we would end up with this. And then we can sort of do this for all of the improvements that happen via X. For these other columns here, I do not need to do anything because they are top, and I'm always projecting on things where the A does not appear. So the only way they will change is if it becomes bottom, any of these values. This was the round for X. Then we do the round for Y. We have some improvements here, again, in these clusters. And then we have at Z, we then get the value that it's bottom, so for this AZ cluster. Then we propagate all of the improvements that can be made via Z. So then we end up with this value here, where we have computed the 2 normalization for all of the values, for all of the clusters in which A appears. However, the algorithm is now done. So we stop, and we have the problem that for this example here, our algorithm has failed to compute this 2 normalization because we have tops everywhere here. So actually, 2 decomposability alone does not already make this efficient normalization possible. So then we tried a different angle and considered this 2 normalization via a constraint system. And once again, here we are given some abstract relation R that is given by these 2 clusters. And we introduce unknowns for each of these 2 clusters. And basically, we try to write down all of the improvements, or the constraints correspond to the improvements that can be made. So we consider the initial value for x, y, and then we consider the improved values if I go via z for all of these variables that appear here. And then we have a small proposition here, namely that the 2 normalization is a solution of this constraint system. This can be verified quite efficiently. You just plug it into the constraints, and you immediately get it. And the consequence of this is that if there is a greatest solution, it is an over-approximation of this 2 normalization. And then we had this observation that what we do when we do this normalization via the Floyd-Warshall algorithm, we actually perform steps that are similar to the things that the constraint system does, provided that one at some point stops considering intermediate improvements that happen via some of the variables in there. And it appears as little as if these variables were projected away, because I'm not considering the improvements that happen via them anymore. And this inspired us to define another property. Namely, we can say that some 2 decomposable domains are additionally too projective, and we say it is too projective when each variable can be projected away using projections onto clusters only. So what do I mean by this? So let's say here I have some relation that is given as the meet of these clusters, and it ranges over some set of variables y and some variable z that I want to project away. And here these yi's, they are from y, or they are this variable z. And then these r sub some cluster speak about values in this cluster only. And this r prime simply speaks about all of the values that are in this, speaks about variables in y only. And then I say this thing is too decomposable if I can do the following. I basically keep the r prime as it is, and then I try to eliminate the variable z by considering all of the combinations that I can make between clusters involving c and clusters involving other variables. So this would look something like this. And then our claim is that for these two projective domains, there is a greater solution of this constraint system that we have considered before. For these domains, this greater solution coincides with the two normalization, and we can actually efficiently compute this by the Floyd-Warshall algorithm. So I just give you a short proof idea of how one might decide to show this. So first of all, we fix some order on the variables. So we just say the variables now go from x1 to xn, and then we define x sub r to be all of these variables with an index in r, and x sub r bar is basically the complement of this. And if once we have defined this, we define a sequence, and in the sequence we say, okay, for the 0th iteration, for all of the clusters, I just meet it together with the single variable clusters that appear there, and then all of the subsequent iterations, I basically make the improvements explicit that happen via this xr. And I do this for all r greater than 0. And then the idea is that once I have made all of these improvements explicit, this xr does not need to be considered anymore. And we remark here that each step in the sequence actually corresponds to evaluating one constraint of the constraint system. It's going to be important a bit later. Okay, so then our proposition here is if I have this S bar as the abstract relation that is represented by this S sub p, then for the elements of the sequence, in the sequence, the value for this cluster will always be smaller or equal to the value for all the single variables that appear in the cluster. And then the last statement is that basically I can represent the value by meeting together all of these subclusters for the r's that I have not eliminated yet. Let's take a look at what this, or how one would prove this. For r equals 0, it basically holds by definition. There's nothing to show here. For r greater than 0, we do it by induction. And the key step here is that one uses two projectivity to be able to consider these meets in isolation. Now this is the proof. I only put it there because we claim that we have an elegant and short proof, and this is the entire proof of this complicated step. I will not go through it and bore you with it, but I just wanted to put it there. So what is the consequence of this proposition? Well, interestingly, if we actually set k equals n, then we have now, as a consequence of this proposition, that the normalization in this xy cluster is equal to the nth iteration of this of the sequence for the xy cluster, meeting this together with the values for the single variable clusters. And because of our first property from the proposition, we can show that this is basically equivalent to the value of this xy cluster in the nth iteration. Okay, so then let's return to the Floyd-Warshall algorithm here. We basically now need to somehow relate this to the sequence that we have constructed and the constraint system that we have constructed. So let's once again consider some input collection and this S bar, which is the normalized value, and then TP, we call this here the result of this Floyd-Warshall algorithm for this input collection. And then the claim is for any of these two clusters, the two normal form is less or equal than what this Floyd-Warshall has computed. And the second claim is that the two-normal form is greater or equal to what the Floyd-Warshall has computed. So basically the claim here is that they are actually equal. How do we show the first thing? Well, the idea is here that the constraint system that I was showing you earlier, all of the right-hand sides of this constraint system are monotonic, and each update of the Floyd-Warshall algorithm corresponds to evaluating one of the constraints. So whatever this algorithm will compute is greater or equal to the greatest solution of the constraint system. And before we have shown that this greatest solution over approximates the two normalization. So this is the first property here. And then the second property, we show this by induction. And namely, what we show is the value in the kth iteration of this Floyd-Warshall algorithm is less than the value in the kth sequence that we have constructed before. And then we have shown these two to be equal here. So now what do we have? Well, we have that the normalization is cubic, provided that we have R that is 2 decomposable and 2 projective. And there's an important second ingredient, provided that the operations on abstract values over 3 variables are in O of 1. So this is this part here that I have marked in red. So this is one of the ingredients that I need. Now I have so far only talked about 2 projective domains. Let's maybe get back to the octagons. And now the claim that we need for the octagon normalization to be cubic is we need to show that the octagons are indeed 2 projective. So I have here reproduced once again this formula that we have as the definition of 2 projectivity. And I will not bore you with the entire proof, but the intuition here is that one can show this to be equivalent to the Fourier-Motzkin elimination of Z from this set of inequalities. And this works over the rational, so this is sort of well known, but it also works over the integers, given that all non-zero coefficients that appear are either -1 or 1. So this means that both the integer octagons as well as the rational octagons are 2 projective. The question is, are there any other domains that are 2 projective? There's quite a few more here. I'd like to particularly point out this 2 variables per inequality domain here, because it is a bit counterintuitive why we say, okay, the normalization here somehow is not cubic, but there's this log squared factor somewhere in there. And the reason here is, in our proof, we were assuming that these operations on abstract values over 3 variables are in constant time, and this actually is not quite the case for this TDPI domain, which is why you get the complexity that we see here. Okay, so what we have thus far is we have a cubic normalization procedure for 2 projective domains. We have shown that octagons over rationals and integers are in fact 2 projective. Now let's maybe turn a little bit to how one can implement guards for 2 projective domains. Here we are restricting to these guards that can be represented exactly by adding a new constraint. For octagons, this would be adding conjunctions of octagons constraints in your guard. And what this corresponds to technically is that you have improved values in some of your clusters. So your values in some of the clusters has gotten smaller. And then, of course, you can run the algorithm that we have outlined before to restore 2 normalization, and this is going to be cubic again. However, it is known that for octagons, one can do better. One can actually do this in quadratic time. Now the question is, does this translate to the notion of these 2 projective domains? And it, in fact, does. So if we assume that some clusters have improved, here we make this additional assumption that these improvements to the clusters, you're not making them to the single variable clusters. This is just so that we can skip this initialization step. It is not a limitation, because if you want to restrict a single variable, you just add it to any of the 2 clusters that you have. But provided this is done, then one can actually run the Floyd-Warshall algorithm only for these variables that have potentially been modified. And this means that if the incremental normalization after adding constraints for m variables is then in O of m times n squared. And for the proof, we rely on the fact that you have already partially normalized the result. So basically, you have already obtained the invariant that you would obtain after the first x set minus v steps. And this already holds, so you basically only need to consider the last v steps here. So we have also quickly remarked on these guards for 2 projective domains. Then lastly, we have also considered linear assignments for octagons. Here we need to make some additional assumptions, namely we require for the sort of numeric domains that we're considering here, that if you have an assignment x equals v, x equals e, then the value for those variables that are not modified by the assignment remains the same. So if I assign to x, this does not magically change the value for some variable y. And conversely, we also assume that if I compute the value for some cluster y that contains x, I only need to consider those variables that are either in y or that appear on the right-hand side. So I do not need to consider all of the other variables that somehow appear. This is a sort of reasonable limitation, but there are relational domains which do not satisfy this. And given this, one can then give this new value basically cluster-wise once again. And I do this by basically meeting together all of the clusters that somehow appear. So the clusters that correspond to variables that are on the right-hand side, and these x, y that I'm considering in this cluster that I'm looking at the moment. And then if the computation on values from R over bounded set of variables is constant time, and x equals e only refers to a bounded number of variables, and R before is normalized, then the normalization of this value can be computed in linear time. Now we have this little thing to check here whether this is actually true for our octagons. And the best transformers for octagons for these linear assignments can be cast as LP problems, where one basically needs to maximize some objective functions subject to the constraints that somehow appear in the octagon, where the objective function depends on the constraint that you're considering. And the observation there, we made an additional observation, namely for closed octagons, one can somehow reduce the number of octagon combinations that need to be considered to those where the sign matches the one that appears in the assignment. This is a small improvement that we have made here. And then when we consider the best transformer for closed octagons over the rationals, then each upper bound can be determined by solving an LP problem. Solving these LP problems as polynomials. If the number of variables in the assignment is bounded, then each LP problem uses a bounded number of variables, and those LP problems can then be solved in constant time, which gives you an overall linear runtime for the case of the rationals. For the case of the integers, this is not the case. So then we have also provided some insights here on the linear assignments for octagons. So the question is, what remains there to be done? And in the future, we would like to study further these two decomposable and two projective domains. So for example, we are now considering whether one can extend them beyond numerical domains and maybe consider domains to talk about heap properties. And the other thing that still remains to be done, we have not actually implemented this yet, or we have a small prototype, but we have not implemented it in a huge code base yet. And it would be interesting to compare whether these insights that we had on these normalization procedures actually lead to any improvements to, say, the implementation in Apron or Elena, or whether the insights or whether the improvements here really are only the simplicity of the proofs. And with this, I'd like to thank you, and I look forward to any questions.
So, is there any question? Yes.
Have you thought about how you will lay out memory for when you organize your octagons in memory?
No. So this is a point that we have not considered here. So this is, I know you're one of the co-authors of this work on these efficient normalization after adding a constraint, and I think there, in the cost model that you consider, the layout is quite crucial. Here in our cost model, we have not considered.
No, okay. So I wasn't being prickly about that. I mean, it's a sort of sobering reflection on the work that we did, is that Azim and I obsessed about the matters of complexity, and then we implemented the octagons, and we were working with quite large octagons, up to about 100 or 200 variables. And we found that the sort of dominating performance issue was cache performance. So we used cache grind on our algorithms. So like a cache miss is worth like about 100 arithmetic operations. So in one sense, we spent like months pushing at the wrong thing. Okay, we got a paper in an FMSD, but it was quite sobering in a way in that we were sort of optimizing too early in hindsight. So I think that makes for a very interesting study within itself.
Yes, yeah, I think it's a very, very interesting question, how to get them to scale practically, yes.
Yeah. Okay.
Any other question? All right.
Well, mine is not really a question, just to point out that there is another operation that might be interesting, which is reduction for octagons, which is the inverse of closure. And this has its own uses, for instance, to provide the user with a reduced output when they want to look at the computed invariants. And it can also be used to have a more efficient equality checking because they are normalization, and maybe also to define a semantic widening. So if you go on along this line of research, you might consider implementing it.
Yep, it sounds very interesting to see if one can get any results there based on this 2D composability.
All right, any more question? Then let's thank Michael.